topic of this video is how to simplify radicals. We're going to talk about principal and negative square roots today. For example, if a is a non-negative number, then that means the square root of a is the principal or the non-negative square root of a. When you notice the negative sign out in front of the root symbol, it's read as the negative square root of a. So to break this down, the symbol itself is called the radical sign. The term under the radical sign is the radicand. And sometimes we see a number written outside of the radical sign, and that refers to the index or the root. When you don't see a number written at all, the assumption is we are looking for the square root of the base a. The whole term is called a radical expression. We're going to start with the product rule for simplifying square roots. If a and b are non-negative, the square root of the product a times b is equal to the product of the square roots of a and b. In other words, if you have bases underneath the radical sign that are being multiplied, the product rule allows for us to separate those factors and place them under their own radical signs. So the steps to simplify are to factor any perfect squares from the radicand. In other words, by separating these factors of a and b, we really are hoping that either a is a perfect square or b is a perfect square. Of course, if they both are, that's fine. But if at least one of them is a perfect square, that is what allows us to simplify the radical expression. So we will write radical expressions as the product of radical expressions, and then simplify if there are any perfect squares. In our first example, we have the square root of 9. Well, you might already know that 9 is a perfect square. So if we use the product rule to show that, we could break down the square root of 9 as the square root of 3 times 3, which some people like to write as the square root of the quantity of 3 squared. In this notation, then it's easy to see that you have a perfect square under the radical and you're taking the square root, so they undo. They are opposite operations. Therefore, the base that remains is the base that clears the radical. So your final answer would be 3. With example 2, we have the square root of 49x squared. So another way that this could be written using our product rule is separating the numerical coefficient from the variable base. 49 you could think of as the quantity of 7 squared, and x squared is the quantity of x being squared. So then you can see that square root and squaring are opposite operations, therefore 7 would clear the first radical, and then the square root of a perfect square means x also clears the radical. So our final answer here is 7x. So basically what we're able to do here is convert from one notation to the other. We're starting with radical notation, and then we're able to simplify. So in order to check the answer, you could perform the opposite operation. So in the beginning, we are square rooting, so the opposite of square root is to raise to the power of 2. That means I could take the quantity of 7x and square it. By doing that, I have 7 times 7 times x times x. 7 times 7 is 49. X times x is x squared. And 49x squared was the original radicand. So you can see how it's fairly simple to check your work. In example 3, we have square root of 16. You might recognize that as the square root of 4 quantity squared. So to undo the squaring with square root, we end up with 4. In example 4, now we've got a negative. Since the negative is outside of the radical, we read this as the negative square root of 144. So the negative sign on the outside is actually indicating multiplication of negative 1. So negative 1 is multiplied by the square root of the quantity 12 squared, because we know that 144 is a perfect square. So the terms that clear the radical, negative is already clearing, and now we can see that 12 squared, taking square root, leaves 12. So negative 12 is the negative square root of 144. With example 5, we have 25x squared. So if you like to think of 25 as 5 times 5, you can see that is a quantity of 5 that's being squared under the radical. And we also have x squared. That's also a perfect square. So the terms that clear the radical would be 5 and x. That would be 5x. With example 6, 100, hopefully again, is a recognizable perfect square. That comes from factors 10 times 10. Now we have to be a little more careful here with our variables. X squared, we know, would be x times x. Y cubed, however, means there are 3 bases of y. So now these are the terms under the radical. Anything that I could write as a perfect square, I'm going to do that. So 10 times 10, that's a perfect square. X times x, that's a perfect square. But notice that we have more than 2 bases of y. So let's group them in pairs of 2, because that would indicate a perfect square. So it looks like we have a perfect square and then a leftover base. So we have a perfect square for base of y, but then one left over. So the way we work with leftovers would be first clear any terms that are perfect squares. So 10 will clear. X will clear. Y will clear. But notice I have a base of y that is not a perfect square. So whatever is not a perfect square, whether it's a numerical base or a variable base, it will need to remain under the radical sign. So our final simplification here is 10xy times the square root of y. To simplify these radicals, we're going to look for perfect square factors. Well, the number 50 is not a perfect square. So one thing that I suggest is we set up what's called a factor ladder. We're going to divide 50 by prime numbers, and I believe we've done this in some previous videos. So it ends with 0, so it's even. I could divide by 2. 50 divided by 2 leaves 25. 25 is not an even number, but it does end with 5, which means it is divisible by 5, which happens to be a prime number. 25 divided by 5 leaves 5. 5 can also be divided by 5, leaving 1. So now what we're really interested in finding over here in this set of prime factors is if there are any 2 of a kind. And here we have 5 times 5, that would be 25. This factor of 2 is on its own. What we have actually generated here are the factors that belong under the root to use our product rule. So I can go back to the original square root of 50 and say another way to write that using product rule is the factor of 25 and a factor of 2 under the square root symbols. This is helpful now because I know that 25 originally over here came from the identical factors 5 times 5. So 25 will clear the radical as 5. 2 does not come from perfect square factor, so it will remain under the radical. So the square root of 50 is equal to 5 square roots of 2. So we can use the factor ladder to help us with all of these non-perfect square coefficients. In example 8, we're starting with 32, and we'll divide by a prime number. Since it's even, I might as well use 2. 32 divided by 2 leaves 16. 16 divided by 2 leaves 8. 8 divided by 2 leaves 4. 4 divided by 2 leaves 2. 2 divided by 2 leaves 1. So now we're going to find all of the pairs of identical factors. Here's a pair of 2. That makes 4. This pair of 2's makes 4. Here's a 2 that is single. That remains 2. Now I have 4 times 4 times 2. If you find any identical factors here, keep making your pairs of identical factors. So I have a pair of 4's that makes 16, and 2 is still alone. These are the factors that belong under the root. So I can say that the square root of 32 is the same as square root of 16 multiplied by square root of 2. The benefit here is that 16, we can easily see, is a perfect square that comes from the identical factors 4 times 4. So 16 will clear the radical as 4, but 2 will remain under the square root. But that's not all we have in this problem. We have some variables written out as well. So one quick way to work with those variables is to divide them by the index. So if I break them apart, first of all, I've got my x squared, I have y to the 7th, and I have base of z cubed. 2 divided by our root of 2 leaves exactly 1. So that means the base of x completely clears the radical. Let's do the same division with y. We're taking the exponent 7 and dividing 7 by the index of 2. That leaves 3 remainder 1. So 3 is the amount of that base that will clear the radical. So y cubed will clear the radical, but the remainder is the exponent with that base that remains under the radical. So under our radical, y to the power of 1 must remain. So when you do this very simple division, the first value tells you what exponent belongs with that base to clear the radical, and the remainder is the exponent that remains under the radical. Let's try it now with the base of z. So 3 is going to be divided by index of 2. 3 divided by 2 is 1, remainder 1. So 1 is the exponent for z that clears the radical, but 1 is the exponent for z that remains under the radical. So it looks like we have a very long answer here. Let's put everything in the proper standard form. So standard form means to write the terms that have cleared the radical first. So let's find the terms that have cleared. 4x, y cubed, and z. Starting with the numerical coefficient, I will write 4 first, and then alphabetically I'll write the variables. X, y cubed, z. And then we'll look for everything that remains under the radical. So it looks like we've got 2, y, and z. So those are the terms that are going to remain under the radical, starting with the numerical portion first, and then alphabetically write your variables. So here's our final answer. We can say that the square root of 32 x squared y to the 7th z cubed simplifies as 4xy cubed z times the square root of 2yz. So it is kind of a lengthy answer, but just break it down, starting with the numerical coefficient first, make your factor ladder, find all the identical pairs. Then work through with the variable bases using this division technique. For example 9, we have a 153 a to the 4th b cubed all under a square root. So I'll start with the numerical portion, 153. Now that is not an even number. It doesn't end with 5. So we need to think of some prime number besides 2 or 5 to divide by. Well, I know that 1 plus 5 plus 3 makes 9, and that's divisible by 3. So this number should also be divisible by 3. Okay. So 3 goes into 15 5 times, 3 goes into 3 1 time. Divide 51 by a prime. 5 plus 1 makes 6. So if the sum of these digits is divisible by 3, then that number is also divisible by 3. So 3 goes into 5 once with 2 left. 3 goes into 21 7 times. Again, this is not even. It doesn't end with 5, but 7 plus 1 is 8. That's not divisible by 3. So this time it looks like 17 is a prime number, so it can be divided by itself, leaving 1. Looking off to the side, I can see I have an identical set of factors. 3 times 3 would make 9. 17 by itself is still 17. So 9 and 17 are the factors of 153. So I'll begin to rewrite the problem. So it will now equal square root of 9 times square root of 17. And then we have our variables, a to the 4th and b cubed. 9 will clear the radical as 3. 17 remains under the radical. To work with our variable bases, remember we are taking the exponent and dividing it by the index of 2 because these are square root. 4 divided by 2 is exactly 2, no remainder. That tells us that that base of a will clear the radical with an exponent of 2. With b cubed, 3 is divided by the index of 2. That gives us one remainder, 1. So 1 is the exponent for b that clears, but this time we do have some base of b that remains under the radical, and the exponent for what remains is 1. So let's clear this up. All the terms that have cleared the radical, here they are. That's 3a squared b. What remains under the radical, that would be 17 and b. So that leaves 17b under the square root. Here's our final answer. In our next problem, we have the square root of 250. So I'm starting with 250. It ends with 0, so I know it's an even number. I could either use 2 or 5. I'll go with 5. 5 goes into 25 5 times, and it goes into 0 0 times. So 5 times 50 makes 250. Now we need to divide 50. I'll stick with 5. 50 divided by 5 gives us 10. 10 is also divisible by 5. That leaves 2. 2 is divisible by 2, leaving 1. Remember, when you end up with 1, you know you're done dividing. So we have a pair of 5s to make 25. 5 times 2 leaves 10. So square root of 25, square root of 10 are the factors that we can use to break down 250. I like to start with the square root first of the term that's the perfect square. Then it's automatically in the proper order. So square root of 25 we know is 5. Square root of 10, we know that can't break down into any perfect squares because of the factors that it came from. So 5 square roots of 10 is our final answer.